5. You got it. 20. Oh, right there. Was there a particular part? It just made you very sad. That makes me very sad. So we just used a formula, it looks like. So you can see that ended up being try doing use substitution. It's all off the screen. There. So starting with that, doing use substitution, you can turn it into this, which gives you something to integrate. So the key, let's look at that and see. So in case you're wondering, like, how did I know to use substitution? Honestly, I didn't know it was going to work. But the clue, actually, anybody know what the clue is that said try it? Joshua? Oh, did it say it? Oh, okay. So yeah, I made these a while ago. If it didn't say it, that's kind of the dead giveaway. It's a composition of functions. So it may not be obvious that use substitution is going to work, but if you have a composition in your argument and you don't know what else to do, try use substitution and let u equal the inside function. It's worth a shot. Doesn't always work, but it worked here. So just in case it doesn't give you that hint. Any other questions? Either about this or anything else on the homework. Oh, yeah. So then once you do that, oh, this was fun. Look at that. Yeah. Don't forget, so then it's a rational function and the denominator does factor. So there's your clue of trying partial fractions. And don't forget, it's not improper. It is degree 2 over degree 2, so you have to divide first before you do partial fractions. So that's where the 1 plus is coming from. Any other questions? Yes.
Can you go over 11?
Yes. Does anybody want more time looking at this? 11. There it is. Is there a certain part here that you had a question about?
How did you approximate it using like the trapezoidal?
So remember, trapezoidal rule, the formula is with equal widths. Remember, it's only equal widths. So it's delta x over 2, because that's basically height over 2. If you think of the formula for the area of a trapezoid. So delta x over 2, and if that's delta x, that's delta x over 2. And then the intervals from 1 to 2, so you're going to start at x equals 1, and then you're going to keep adding delta x. That's where all these other values come from. And then the formula says to double all of these, but not the endpoints.
Wouldn't that be like the area though?
Yeah, but that's what trapezoidal rule is the area under the curve.
Wait, but isn't it asking for the arc length?
Oh, so, but trapezoidal rule, so once you set up the integral for arc length, this also represents the area under this curve. So, any other questions? Arc length and surface area is fun! All right. Well, today we're going to do something new. We're going to do Taylor polynomials. What's that? I know, right? And Maclaurin polynomials. Yeah, go ahead and pass up your homework.
Welcome. I wonder if this math was not easy. It would be a shame if somebody didn't do it. I did it. I know. And I wonder if most of them do it. Yeah, I wonder.
That was me. I just came in. And as you already know, no reality check, so we are just
Why should you just take out a real apple?
All right. Today is January 11th. Oh, it's my mommy's birthday. All right, Taylor Polynomials. Let's do this thing. So, oh my goodness. Okay. So, what is a Taylor polynomial? Well, before we start with that, we're going to say that P of X is a polynomial. A sub n are the coefficients, and C is a constant. You'll see what I'm going to do with this in a moment. I can write any polynomial as, it's called a power series, but we don't have to worry about that. But I can write it like this. A sub 0 plus a sub 1 x minus c to the first power plus a sub 2 x minus c squared plus a sub 3 x minus c cubed. And hopefully you can see the pattern here until we get to a sub n times x minus c to the nth power. So every polynomial can always be written in this form. So what can we do with this? I mean, obviously the a sub n's, they're going to be various values to make it work. Well, you know what? Just for fun, I mean, this is calculus. Let's take the derivatives. Why not, right? Why? I don't know. Because it sounds like fun. So, excuse me, the first derivative. Well, the first term, a sub 0, that's a constant, so derivative of that's going to be 0. The derivative of the next term, a sub 1 times x minus c, that's just going to be a sub 1. The derivative of the next term would be 2 a sub 2 x minus c to the first power. The next term would be 3 a sub 3 times x minus c squared. The next term, if we had it written, we could see it, but I think you guys see a pattern anyway. It'd be 4 a sub 4 x minus c cubed. And you just keep going. You'll see I don't really care about the other terms. That was so much fun. Let's do it again. Yeah. Let's find the second derivative. Actually, I'm going to skip a space. The second derivative. Well, again, the derivative of the first term now is just a constant, so that's going to be 0. The derivative of the next one is just going to be 2 a sub 2. The next one is going to be 6 a sub 3. Actually, let me not write it as 6. Let's write it as 3 times 2. Just for some crazy reason. I don't know. The next one would be 4 times 3. Oh, sorry, that should be... Oh, no, that's right, to the first power. Lost where I was. 4 times 3, a sub 4, x minus c squared, and, you know, this would just keep going. And I'm having a good time, so I'm going to keep going. I'm going to take the third derivative. Let's do this a little faster now. Derivative of the first term is 0. The next one's just going to be 3 times 2, a sub 3. The next one's going to be 4 times 3 times 2, a sub 4 times x minus c plus c. And I'm only going to go one more, but let's go one more. Let's find the fourth derivative. So that's going to be 0, the first term. The next one is just going to be 4 times 3 times 2, a sub 4 plus... Good times, right? Yeah. So any questions just where all that's coming from? I know you probably have no idea where I'm going with this. That's okay. All right. So now I have these 5 equations here. Let's evaluate each of the 5 equations. Evaluate the above equations at x equals c. So let's see. So P of C. Oh my God, we got to plug C into all those x's? That's going to take forever. Yeah. Or is it? Because all those x minus c's, if x equals c, turns into 0, it's just going to be a sub 0. And then P prime of C is just going to be a sub 1. And then P double prime of C is just going to be 2, a sub 2. And P triple prime of C is going to be 3 times 2, a sub 3. And the fourth derivative of P, evaluated at C, is just going to be 4 times 3 times 2, a sub 4. Ah, do we see a pattern here? Okay, so if I were to generalize for the nth derivative, what could it be? Does anybody see it? It's okay if you don't. Hear it?
I don't know how to, n, okay, it should be like n times n minus 1 times n minus 2, etc. down to 2 of a sub n times a sub n.
All the way times 2. And actually, we can even go to 1 just for fun. Yeah?
N factorial a sub n.
Yeah. So that whole, if you haven't seen it yet, if you've taken stats, you've definitely seen it. If you haven't taken stats, you may or may not have seen it. But that whole 5 times 4 times 3 times 2 times 1, or 7 times 6 times 5 times... If you started an integer and you go down multiplying until 1, that's called factorial. The notation is this exclamation part, but you don't say n! It's n factorial. You could. That's true. And it's fun to say. I have to say. Any excuse to yell. That's what I say. So, like this fourth derivative of p at c, 4 times 3 times 2, that's just 4 factorial a sub 4. 3 times 2 times 1, that's just 3 factorial a sub 3. This is just 2 factorial a sub 2. This is just 1 factorial a sub 1. And believe it or not, 0 factorial is defined as equaling 1. And I always have a brain fart every year, and I always mean to look it up, and I forgot. There's an easy way to demonstrate why 0 factorial is 1. Anybody happen to remember what it is? I know there's a couple ways, but there's like one that's really easy. I just can't remember it. All right. Anyway, just go with it though. 0 factorial, even though it seems like, wait, should it be 0? What? No, it's 1. It's kind of like 2 to the power of 0. Why is 2 to the power of 0 1? You're not multiplying any 2s. Should it be 0? Anyway, so there is a reason for it. I just can't remember it. So yeah, this guy right here, this nth derivative of p at c is just n factorial a sub n. Dun, dun, dun. So we can actually take this equation that we just got at the bottom here and solve for a sub n. And this gives us a way to rewrite all the coefficients in that polynomial that I gave you. And that, so it's going to be a sub n equals the nth derivative of p evaluated at c over n factorial. That's actually important, even though it may not seem very important right now. But any questions how I got there? Because what we're going to do with that, we now have a different way of writing a sub n. So if I go back to this original polynomial that I had in blue and replace all of these a sub n's with what we have below, we have a way to write the nth term, and it will actually be a nice, lovely way of doing this. And that's actually what a Taylor polynomial is. So let me write this down a little more, slightly more formally. It won't be that big of a bubble. You know I like my bubbles. But an nth degree Taylor polynomial we'll say t sub n x of x. That's the way of notating an nth degree Taylor polynomial. To approximate f of x at values close to x equals c is t sub n of x equals. We're going to just write it as a summation, and that'll take care of all the terms at once. So let me go back to the polynomial that we have at the top of the page for a second. If you look at every single term, like the nth term, is a sub n x minus c to the nth power. And we now have a way of writing a sub n. That was this thing right here. So we're going to say k equals 0 to n. And then I'm basically going to write the formula we have above. The k, whoops, that's supposed to be a p. The kth derivative of p evaluated at c, and actually I did want to f, my bad, over k factorial times x minus c to the kth power. And just a little note, a Maclaurin polynomial is a Taylor polynomial centered at x equals 0. I'll let you write that down, but then I'll tell you what it means, because I know it may not mean much right now. But it actually ends up being pretty cool. It'll be easier to explain what it means with an example. So that's what we'll do. All right. So I'm not going to ask if there's any questions, because I'll bet there are. So let's just do an example. Example. Find a Maclaurin polynomial for y equals cosine x. Now, the wording here doesn't tell us what degree to go to. If it doesn't tell you a specific degree to go to, then generalize. And you're going to like have something that would represent any degree. You're going to go to an nth term. You'll see what I mean by that. Sometimes a problem will tell you a specific degree. Sometimes it doesn't. All right. What we need to do in order to do this, we need to find the derivatives. You basically find the derivatives. It's grunt work. You have to do it. You just go through finding the derivatives and evaluate them at C and look for a pattern. And a lot of times there is. Sometimes there isn't. Depends on what you got. You're going to see there's a very nice pattern that pops up here. But that's going to give us something to plug in here, and then the k's just depend on the term you're at. You'll, again, see what I mean here. So we're starting with f of x equaling cosine x. It's a good idea. Go down to like the fourth derivative, and then you evaluate. So we know that f prime of x is negative sine x. F double prime of x is negative cosine x. The third derivative is sine x. The fourth derivative is cosine x. Definitely a pattern here. Sometimes you see the pattern just in the derivatives. Sometimes you don't. Sometimes you don't see a pattern until you actually start plugging in the C. And then even then, sometimes you don't see a pattern. But now we're going to evaluate. According to the cloud, come back here. According to the cloud up above, can you guys see what C equals? Because remember, now we got to plug in C to all these derivatives. It doesn't actually say C equals, that's why it's not so obvious. Greg? It is 0, yeah. So when we say centered at a value, that value that you're centered at is C. And again, I know it probably doesn't make any sense what it means to be centered at. Let's finish this example and I'll kind of explain everything as we go on. But it says centered at this value, this is your value of C. So C equals 0. If it's a Maclaurin polynomial, C equals 0 automatically. So f of C is 1, f prime of C is 0, f double prime of C is negative 1, third derivative is 0, fourth derivative is positive 1. Definitely a pattern happening here. All right. So we can see now the derivatives are just going to go 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0. And we'll just plug it in and see what we get. So any questions there? Okay. So now let's go ahead and write our Taylor polynomial. Normally we wouldn't have to do this sigma, but I'm doing it here just so we can have it as a reference because it's scrolled off the page. So remember it's k equals 0 to n of the nth derivative evaluated at c over, oh, sure, I need a k there instead. K derivative over k factorial times x minus c to the k. So, let's start with k equaling 0. If k equals 0, then we have the 0th derivative is like the function itself. So that's 1 on the top over 1 factorial times x minus c times 0 factorial, sorry. Anyway, let me write it out. We got 1 over 0 factorial times x minus c to the 0th power. And then, k equaling 1, so we're going to go to the first derivative. And it's going to be 0 over 1 factorial times x. It's going to end up being 0. That 0 makes the whole entire term 0. So I'm just going to put 0. Then k equals 2. So we go to the second derivative. So it's minus 1 on the top over 2 factorial times x minus c squared. So minus 1 over 2 factorial times x minus c squared. Then be plus 0 again. Then plus 1 over 4 factorial times x minus c to the 4th power. So any questions where I'm getting all that from? Because now when we simplify it, you can see a very nice pattern. First of all, what is c again? So I could have been plugging in 0 there. What's that first term equal to? This term right here. Yes, just 1. I'm not going to write the plus 0 this time. So let's go to the next term. How can I write the next term simplified? 1/2 x squared. 2 factorials, 2 times 1. So this is 1/2 x squared. 1/2 x squared. I'll say x squared over 2 minus x squared over 2. Not going to bother with the 0. Let's look at this guy. Yeah. We can write 24, but as it keeps going, these numbers are going to get kind of big. I'm actually going to leave it as 4 factorial. So x to the 4th over 4 factorial plus x to the 4th over 4 factorial. And then we'd have another term with a 0. And then it would be minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial plus, minus actually. And it would just keep going. Kind of nice, huh? Let's see if we can find a way to represent the nth term. We're going to generalize. So if this is the first term, second term, third term, fourth term, fifth term, how can we generalize to the nth term? Well, the exponents, we go from 0, 2, 4, 6, 8. Think of it this way. That's the first term. That's the second. That's the third. So this is like, if I go to write this as a sigma, we have n equals 1, n equals 2, n equals 3, and so on, n equals 4, n equals 5. So when I go to my nth term, the numerator is x to some power. What can that power be in terms of n? Yeah. You could write it as 2n minus 2. And now now you see the numerator, or the exponent. What's the denominator? How can we write the denominator? Yeah. 2n minus 2 factorial. Now I left a little space in the front because we have to take care of the alternating signs. But that takes care of the terms themselves. The alternating signs come from doing -1 to some power. What do you think we could write the power as? To start with a positive, then go negative, positive, negative, positive. Yeah, I heard n minus 1 or n plus 1, and those are the two common ones. And, I mean, you really could do n plus any odd integer. N plus 1 or n minus 1 are the ones that are used, just for obvious reasons. You pick, it doesn't matter. And there it is. So, if we were to generalize this as a sigma, and sometimes it wants to and sometimes it doesn't, it just kind of depends. And actually I'll go ahead and say plus ... This thing keeps going then. So if we say n equals 1 to infinity, that's our argument right there. Negative 1 to the n minus 1 times x to the 2n minus 2 over 2n minus 2 factorial. And we could write this another way. And you'll see both ways. Probably the other way is actually a little more common. Instead of starting at 1, we can start at n equaling 0. We'll have to make some slight adjustments though. How will my exponent on the negative 1 change to make it alternate starting with positive, negative, positive, negative? Or will it change? Maybe it doesn't. I don't know. If it didn't change, if it was n minus 1, but we start with 0, it'd be negative 1 to the negative 1 power. That would actually mean starting with a negative value. We don't want to do that. We're supposed to start with positive. So how can I adjust that exponent? Yeah, just make it n. Do I have to adjust the other exponents? If I start with 0 but still use this exponent, that would be x to the negative 2. Is that what I want? Should be 2n minus 1. Make that. Yeah, is it just 2n or 2n minus 1? One of those is correct. Just test it out. Yeah, 2n minus 1, you'll get used to it. That actually means all the odd numbers. We want even exponents. But if you let n equal 0, your first term should start with x to the negative 1 power. Does our first term have x to the negative 1 power? No. We want x to the 0 power. So it is just going to be 2n. So in the bottom then it's just 2n factorial. And you can see that this version ends up being a little simpler. That's why a lot of times we'll start with 0 instead of 1. But technically both of these are correct. We still have no idea what we found, but we found it, damn it. Yeah. Now we're going to figure out what the heck this means now that we have something to play with. But any questions how we got here? All right. Here's what it all means, and I'll show you with Desmos visually now that we have something. I'm going to go back up here to the definition, to the cloud. Polynomials are easier to work with than something like trig, which is what we were just doing. If I want to evaluate a polynomial, the arithmetic involved in that, much simpler than trying to do a trig function. And so if we can turn these other functions into polynomials, the number crunching becomes much easier. It's actually more efficient for computers and calculators to do it this way too. And it turns out we can. These Taylor polynomials help us come up with approximate values for these other functions like trig functions or log functions, other transcendental functions. So that's what this Taylor polynomial is going to do for us. But when we say centered at a value, this Taylor polynomial is going to give us pretty good approximations. Because the one we just found is centered at x equals 0, it's going to give us pretty good approximations for values of x close to 0. The further we get away from 0, the worse the approximation is going to get. And the cool part is, these polynomials actually, with just a few terms, can give us really good approximations. Let me go to Desmos. So we have y equals cosine x. That's what we're trying to approximate. Now, we just approximated it with this Taylor polynomial. Y equals, and our first term was 1. Now, with just one term alone, if we look just, remember this is centered at x equals 0, so we want to focus where x is equal to 0. With just one term alone, that's actually, as long as we're close to 0, that's not a bad approximation. I mean, if I scroll in far enough, you may be going, what? That's terrible. But if I scroll in enough, as long as I get really close, they're pretty close to each other, aren't they? Not so bad. But can we do better? And we can if I go ahead and add another term. So the next term that we found was x squared divided by 2. Look at it. That's actually, again, as long as we're close to x equals 0, they're pretty close. What happens if we go ahead and add x to the 4th divided by, I don't know if Desmos knows factorial. Ah, it does. Look at that. It's pretty good. I'll just go one more. Minus x to the 6th divided by 6 factorial. I lied. I'm going to go one more. This is too much fun. So as long as we're close to where we're centered at, it's pretty good. That is not bad at all. That's what a Taylor polynomial does. A Taylor polynomial gives you a polynomial that approximates some other function for values close to x equals c. And a lot of your calculators actually use stuff like Taylor polynomials and these other forms of, like, I don't know if you've ever wondered, how does my calculator know what the cosine of 3.7 is? What is it doing? It's doing stuff like this. So it's kind of cool. So that's what it is. Yeah. Taylor polynomials give you an approximation for values of x close to x equals c for some other function. Oh, and then what we'll look at today, because you may wonder, well, how do we know how close we are? How do we know if close enough, like how many terms is it going to take to get close enough? And we do have something called an error bound that's going to help us with that. We're actually going to see that by the end of today. So now that you've seen this, any questions what a Taylor polynomial is? All right. And yeah, look, that only took 5 terms, and we're pretty, I mean, now we're actually, this, if you get into like 3 units away from C, that's actually considered pretty far away from C. But it only took 5 terms to get really close. Anyway. All right. So that was that one. Let's go ahead and see now. I'm going to go back to the notes. Maybe. There we go. So now that we have a Taylor polynomial for, actually, let me back up one quick second. Get used to when we get to our unit on series. We're going to be doing a lot of sigma notation, a whole lot of sigma notation. So kind of get in your brain about how to write your polynomials in terms of sigmas. But as far as how to write your final answer, do you have to write it like we had it there at the top of the screen where it's written in individual terms, or do you have to put it as a sigma? The answer is, you pick. Unless the directions tell you specifically write it as a sigma or show each term, you get to pick how you want to put your answer. That doesn't matter. So we're actually not going to use sigma after this for our notes. Oops, over here. All right, so now that we have a Taylor polynomial for cosine, let's actually use the 4th degree Taylor polynomial, t sub 4 of x, from above to approximate cosine of 0.3 and cosine of 1.3. So let's see this. So when you see the notation like this, t sub 4, it's the 4th degree polynomial. It doesn't mean the 4th non-zero term. It means the 4th degree polynomial. So for this guy right here, we're going to go just to this 3rd term when we're at the 4th degree. So it's 1 minus x squared over 2 plus x to the 4th. You can write it as 4 factorial. You can write it as 24. Either way is totally fine, and not really, one way is not really considered more simplified than the other. I won't care which way you put your final thing. That's what we're going to use. And so let's go ahead and do it. We're going to find, oops, not that. The 4th degree Taylor polynomial evaluated at 0.3. That's going to tell us an approximation for cosine of 0.3. And then cosine of 1.3, we're just going to plug in here. And I'm going to go to the calculator and just show you something to make life a little easier when you're doing homework or whatever. So let me... Why are you beginning? There we go. So remember how you can, I think this is locked. Yeah, hang on, my calculator is not working. Yeah, Kieran.
Didn't we have an x minus c term in the beginning?
We did. It was x, but remember, a Maclaurin polynomial is centered at x equals 0, which means c is equal to 0. So x minus c becomes x minus 0.
Are we not equating c to 0.3 now?
No, we are not. C is still 0, but now we're going to let x equal 0.3.
Okay.
All right. Now I think I can go ahead and, yay, now I can click on buttons and it works. All right. So just to make my life easier, since I'm going to take this polynomial and evaluate it at more than one thing, I'm going to go ahead and use the fact that I can store in for variables. I can put 0.3 in for x, and then just type in the polynomial with an x. So 1 minus x squared over 2 plus x to the 4th. When these numbers start getting kind of big, it can be a pain. I mean, 4 times 3 times 2 isn't that hard to work out, but your calculator actually does have a factorial. It's hidden under the math button. So if you click on math, you have to go over to probability on the top. But you go over there, and choice number 4, there's your factorial. So there's the approximation right there. I'm just going to make a note of that in our notes here. And then all I have to do now is 1.3 store x, and then do that second enter, second enter. Of course, I like the furthest apart on the thing. There's a polynomial again, and just hit enter, and now it reevaluates. So makes life a little easier. And just for fun, let's see what the, I say actual values. The value it's going to show us up here is actually still an approximation. But let's see what the calculator says cosine of 0.3 is. Look at that. This was our approximation. Look, we got 1, 2, 3, 4, 5 digits. Correct. With just 3 terms. What? This is crazy. I'm just writing this down too. And then if I do cosine of 1.3, Do you expect this to be as good, better, worse? Why is it worse? That's further. Very good. Exactly. And you can see it is a little worse. Yeah. All right. So any questions on the calculator before I go back to our notes? All right. So I just made a note of all those numbers. They're here. Oh, yeah.
Why is it that we didn't use n equals 4 like we did above? We labeled each other column or each term, yeah. Each term, we scroll up to like n equals 4.
So it's the notation thing. Yeah, when, how did I word it? Okay, so if it says, when it says this, like, in the T sub whatever, that's telling you specifically the degree to go to. So go to the 4th degree.
Oh, okay. Thank you.
Yep. Any other questions? Oh, yes.
When a problem goes to approximate like a cosine 1.3, for example, using Taylor series, would you use 0 or would you use 1 or C?
Ah, that's an excellent question. If you have a calculator, use 1, because that's closer to 1.3. But if you're doing this by hand, use 0, knowing that it's not going to be as good an approximation, because cosine of 1, I don't know what that is. We're just running into the same problem, trying to find cosine of 1.3. If we're trying to find cosine of 1. And so the idea is that we're using these known values to help us approximate these unknown values. Because remember, to derive that whole thing, we had to take all the derivatives and be able to evaluate those at C.
Oh, yeah.
So to evaluate these at 1, I don't know what they are. Any other questions? Yes, Matthew.
Why do you only use 3 terms?
Because this notation right here is telling us to go to the 4th degree. So we stop when we get to x to the 4th power. Any other questions? Yes.
So in this notation, it would be like impossible for 4 to be replaced by 3, right? We wouldn't be able to do that.
Well, actually, I mean, it might. And then you go, I mean, the third degree term is just 0.
Okay.
So
It looks like we won't like that.
I wouldn't say that. Because sometimes we go, I mean, we're doing ones with nice patterns and stuff, but then what if you're using a function where you don't know going into it what the actual values are going to be. So you may run into that last term or last few terms being 0 and you say, oh, okay. Any other questions? All right. I'm going to have you guys try one. I can find my phone. There it is. Example. You guys try finding the 4th degree Taylor polynomial for y equals the natural log of x centered at x equals 1. Give that a shot. I'm going to pause the recording. Here's all the derivatives. So if you want to check your first step. I'm going to pause. So remember, in general, each term of a Taylor polynomial is the nth derivative over n factorial times x minus c to the nth power. And so that's what I was doing each time. Is this in your way? Does this get in your way? Okay. So then I might as well, I've got it there. Here it is, simplified a little bit. Those fractions are going to simplify, so we don't have factorial anymore. So just kind of trust in the formula. Just go with it. And get used to the nth derivative over n factorial times x minus c to the nth power. And then if you wanted to find approximations for values close to 1, you let x equal whatever those values are, and you plug them in, and voila. I'm forgetting my x. Any questions about this? Because now we're going to get into error.
The final function always going to have a pattern.
Say it again?
Is the final function or the approximation is it always going to have a pattern?
Always going to have a power?
A pattern.
No, not always. The ones we'll deal with mostly this year do, but they don't have to. Where did what come from? Oh, that's me being silly. That's me pulling a show in here, sorry. Good catch. I was just seeing if you guys were paying attention again, so good job. Yeah. I have to do those little tests every now and then. Make sure you're awake. All right. Let's talk about error versus error bound. Yes. Error. Okay, what does error mean versus error bound? Well, error is how off were you? How far away is the approximation from the actual value? So error, how bad is it? Error bound is the maximum difference expected between the approximation and the actual value. In other words, error bound is the maximum error. Or you can simply just say the maximum expected error. So you find error, you find the value of the error after you've got your approximation. But to find the error, the actual error, you have to know what the actual value is. But we're doing these approximations often because we don't want to find the actual answer. If we knew what the actual answer is, why do we need to do an approximation? But how bad is our approximation? So the error bound helps you find that without actually knowing what the actual answer is. Actually. What does all this mean? Let's do one more problem where we're going to investigate error versus error bound. Any questions just on the definition? To find error, that's actually really easy then. Error, so now we're going to look at formulas. A formula for the error, that's the difference. That's the difference between the actual value and in this case, the approximation using our Taylor polynomials. But if I just leave it like this, depending if my answer is a little bit under or a little bit over, I might get a positive or a negative answer here. We don't really care about the positive or negative when we're talking about error. It's just how far away is it. So I'm going to put this in absolute value symbols. And that's error. That's all you have to do. You just subtract and drop the negative if it's there. Error bound, though, that formula is a little more fun. The formula for error bound is this. And actually, I'll specify that this is the error bound for Taylor polynomials. We're going to look at error bounds for a couple of different things throughout this semester. So the error bound for Taylor polynomials is this. The error that you get, which again is this, will be less than or equal to this thing. Just write it down. I'll explain it to you. It's going to look crazy, but it's not that bad. K times the absolute value of x minus a to the n plus 1th power over n plus 1 factorial. But I have to define a few things. To tell you what the heck is k, where k is the max value of the nth plus 1 derivative evaluated at u. Not me, you. Ha ha. Well, what the heck is u? Where u is between x and a. What is this madness? Well, I'll tell you. Again, this will be easier to explain going through an example. So just write the words down and we'll figure out what it is. Let's go purple. Anybody still need this? Okay. So let's look at this guy. Last example. Let's use the 4th degree Taylor polynomial to approximate the natural log of 1.2. And actually, we have the 4th degree Taylor polynomial for natural log of x. We just found that in a previous problem. So I'm going to do a little cut and paste here. Snag this guy. Let's put it down here. So we just found that above. So all I'm going to do is use a calculator. And put in a 1.2. You guys try. I'm not going to write it. Letting all those x's equal 1.2. You guys try it too. We'll see if we get the same answer. Oops. You guys check my work, make sure I didn't make a mistake typing stuff in. You guys get the same thing? Alright. So let's find the error and the error bound. Which one should be bigger? Using the definition of error and error bound, which should be the bigger value? Error or error bound? Error bound, very good. Alright. How are we going to find the error? Yeah, just subtract. The error is going to be the natural log of 1.2 minus the fourth degree Taylor polynomial evaluated at 1.2, but let's take the absolute value. So I'm just going to subtract natural log of 1.2, and I'm getting a very small answer. 5.489 times 10 to the negative fifth. That was not that far away. That was pretty darn close. Okay, now let's do error bound. Error bound says that the actual error, I'm just so excited about drawing R's. The actual error should be less than or equal to, come back here, oops, k times the absolute value of x minus a to the n plus 1 over n plus 1 factorial. Let's see if we can find all these values so we can plug them in. So first of all, what are we going to let, what does n equal in this problem? It equals 4. It's whatever degree polynomial is that you're using. What does x equal in this problem? Actually, no. It's the other one. Yeah. X is the value that we're approximating at, and then a is what we're centered at. Doesn't really matter because there's the absolute value there, but technically that's what they are. So now it's just up to this k. What the heck is the k value? And remember, k is the max value, max value of, and I'm just going to take the wording from above and then we'll like plug in the max value of the fifth derivative of u where, remember it says up above where u is between x and a, in this case where u is between 1 and 1.2. Sorry, that's smushed. Move it over just a little bit. So we need to find the fifth derivative, but that's actually not a big deal. I'm going to go back to our work from the problem where we found this polynomial in the first place. Back up to here. The fifth derivative, well, that would just be negative, -2, -3, -4 times x to the negative fifth power. That's just 4 factorial x to the fifth. So I'm going to go down here now. So the fifth derivative of x is 4 factorial over x to the fifth. Stop me if this isn't making sense. Any questions? Now, we're finding an absolute max. Use your things that you know from Calc AB about how to find the absolute max in a given interval. We want the absolute max of that function on the interval from 1 to 1.2. It's actually not that hard if you think about it. Anybody have an idea how we can approach this? Don't just mindlessly like follow the steps you did from last year, but think about it. We're talking about such a small interval. This often happens. Not all the time, but often. Look at the function. On the interval from 1 to 1.2, is that function always increasing or always decreasing? It's always something. I just didn't hear what you said. So if I'm going from 1 to 1.2, yeah, it's always decreasing. The denominator is going to get bigger while the numerator stays the same. So if the denominator gets bigger, the whole fraction gets smaller. This is a decreasing function on that interval. So if this is a decreasing function on that interval, we know the max value happens at x equals 1. So let me write that down in our notes. This is always decreasing on the interval from 1 to 1.2. So we're going to let k equal the fifth derivative evaluated at 1, which is just 4 factorial. So that's the kind of thinking you're going to want to do about k. Now we have everything we need. Now we're just going to plug into the function. Any questions how we found k? K. All right, we're going to go back over here. So error is less than or equal to k, which we now know is 4 factorial. The absolute value of x minus a, that's 1 minus 1.2 or 1.2 minus whatever. It's just 0.2 to the fifth power over 5 factorial. So when I work this out, by the way, this does simplify. What's 4 factorial over 5 factorial? 1/5. This is just 0.2 to the fifth power over 5. So we get 6.4 times 10 to the negative fifth. And if you compare our error that we actually got to this, yeah, we were within that. So there you go. So notice, by the way, notice we could have found the error bound without knowing the actual answer. So this is how you can find out how close your approximation is without knowing the actual answer. We know that our approximation is got to be less than that. It doesn't tell you the actual error, but it tells you the bound. So, any questions about that? Taylor polynomials are fun. They're kind of weird. They're kind of cool. All right, I'm going to stop the recording and we